next speaker is Arthur, who will tell us about Cryptis.
Yeah, if you want that. That's a bit too high.
I think it might be better in the...
Yeah, because it was a bit too high.
Hello?
Right on the left.
Let's see.
And then he has to turn
That's
it
a
around.
bit...
Yeah.
I think just use
Well,
this.
let me...
Hello.
Okay, good. So like many stories, our story today starts with two characters, Alice and Bob, except that because we're in France, we should actually call Bob B. We're going to stick to Bob anyway. In any case, Alice and Bob own nodes in a network, and Bob has a server that stores some integer that Alice wants to know. So Alice sends a request to Bob asking for this value, and then Bob replies with the answer. Now, if this is taking place over a private network, where these are the only two nodes, then Alice can be fairly confident that the answer she got is accurate, that it reflects the integer that is stored in Bob's server. But now, let's assume a slightly more interesting scenario, where this is taking place not over a private network, but over a public network. Now, when we send a message, this message is not going to be relayed directly to the person we want to talk to. It's going to be relayed over a series of intermediate nodes that could be, for instance, controlled by attackers. So the attacker might be able to intercept Bob's message and replace it with some other value, tricking Alice into believing that something incorrect is true. So what can Alice do to prevent this kind of situation? Well, one solution is to use encryption. So now, instead of replying to Alice with a plain text message, Bob is going to encrypt his response using a symmetric key that is known only to himself and to Alice. Now, when Alice reads this message, if she managed to decrypt it, she can know that the answer is accurate because there's no one else that could have produced this message. If an attacker tries to trick her into believing that an incorrect value is the correct one, he will not be able to do that. Now, if we were to consider a slightly more realistic setting, where we might deploy something like this, we would see that it would be more complex along many axes. For the first thing, it will generally not be the case that Alice can start talking to Bob right away. She might have to initiate some kind of authentication protocol to prove her identity to Bob, and also to exchange some session key with him that she can use to encrypt the communication. When the communication starts, what they're going to exchange is typically not going to be a simple call and response pattern. We're going to have several messages flowing back and forth. And also, the logic of the actors themselves internally might be more complicated. For instance, Bob might not be a monolithic server, but it might be some kind of distributed system that it's running its own protocol. And we'd like to make sure that despite all of this complexity, everything behaves correctly from Alice's point of view, even in the presence of evil attackers. So how could we do this? Well, because this is the separation logic session, I guess it won't come as a surprise that we might attempt some kind of formal verification. And in particular, we might attempt to reason compositionally, right? So maybe we could say, okay, let's formally verify the protocol that is allowing the agents to communicate, and let's formally verify whatever application logic is sitting on top of this protocol. And then we can just put the two together by composition, and everything works. That would be great, except that if you were to try to do this in practice, you would face several obstacles. One obstacle is that the tools that you would use to verify each piece of the puzzle don't really talk to each other. To verify the application logic, we might use some kind of general purpose proof assistant or verification programming language. But to verify the protocol bits, you would typically resort to domain-specific tools. These tools are great for verifying correctness properties of cryptographic protocols, but they don't really talk to these general-purpose tools. So we wouldn't be able to compose the correctness results. Even if we were able to compose these results, we would face a different obstacle, which is that the notion of correctness that we use for cryptographic protocols was not designed with reuse in mind. So for a cryptographic protocol, typically we would like to prove that when agents authenticate with each other, they can prove their identities to each other so they know who they're talking to. And we might also like to prove that the session keys that they exchange are secret. On the application side, we might like to prove an application-level property, such as showing that every read that we get back from the database reports the correct value. And we might be able to prove this using some kind of reliable communication abstraction, but it's not clear how we might substantiate that this reliable communication abstraction is correct based on just the properties that I enumerated there for the cryptographic protocol. And this leads me to the work that I'm presenting today on this Cryptis logic. Cryptis is an integrated logic for proving properties of systems that include cryptographic components. And it's built on two core ideas. The first idea, which intersects with other related work in this area, is that we should be able to enable the reuse of protocol proofs by leveraging advanced features of separation logic in the so-called symbolic model of cryptography. So as you might be aware, separation logic is nice because it's an expressive program logic that enables compositionality by focusing on resources and coordination and independence of resources. Symbolic cryptography, on the other hand, which I guess less of you are familiar with, is a paradigm for reasoning about cryptographic code in which we assume that agents can communicate over a network, but that the network is controlled by attackers. These attackers are capable of manipulating messages arbitrarily, but in doing so, they're bound by an assumption of perfect cryptography. So this means that when I receive a message and I try to decrypt the message, the decryption will only succeed if I have the key that matches the encrypted message. Moreover, it should be impossible for me to simply guess this key out of thin air. I can only generate a key myself from scratch, or I can get an existing key from somebody else. Once I have a logic that has these two parts, symbolic cryptography and separation logic, I can use these features to verify the cryptographic protocol, verify the application logic on top of it, and put the two together. But this only works, as I was mentioning earlier, if we have a notion of correctness for cryptographic protocols that allows this kind of reuse. This is where the second idea comes into play. We take inspiration from prior work on the verification of distributed systems, and we argue that the specifications for cryptographic protocols should really allow agents to coordinate on the use of separation logic resources. And of course, because we would like this whole thing to be built on a minimal TCB, Cryptis is designed as a library on top of the Rocq proof assistance and of the iris separation logic. So in the remainder of the talk, I'd like to give you a brief tour of Cryptis and show what kind of examples we can verify with it. I'm going to work with the hello world of protocol verification, the Needham-Schroeder-Lowe protocol. In this protocol, Alice wants to authenticate with the server Bob, so what she does is that she sends a message to Bob encrypted under Bob's public key. And this message contains a fresh nonce that Alice just generated along with her public key, which serves as her identity. Assuming that Bob wants to accept the connection, he's going to generate a nonce of his own and reply it back to Alice with a similar message. And then finally, Alice confirms the end of the handshake by sending Bob's nonce back to him. We'd like to prove the following spec for the function that Alice runs. What does the spec say? Well, we start out by assuming that the public keys of the agents are indeed public. In Cryptis, we have this special public assertion, which describes things that can be sent over the network. And because they can be sent over the network, they can be inspected by attackers and manipulated by attackers. We also assume that the private keys of the agents are kept secret. For those of you who are familiar with Iris, you will notice that here I have guarded these negations with the persistence modality, which means that negation behaves as a logical assertion and not as a separation logic resource. In any case, assuming that the initiator code terminates, we're going to get two nonces back, an A and an B, that are guaranteed to be secret, and we're also going to get some application level property phi that holds of the identities of the agents and of the nonces that they just exchanged. What's novel here is that this assertion is not a traditional logic assertion. This can contain arbitrary separation logic resources that tie together the agents and the session that they have just initiated. In the paper, you also see a more general situation where we're talking to an agent who's not necessarily assumed to be honest. So let's see how this proof goes. Here I have the code that I'm verifying, the current proof state, and the end goal that we're trying to achieve. To do this proof, we're going to rely on Cryptis rules that expose the reasoning principles behind symbolic cryptography, but allow us to use separation logic resources in them. So let's see how that works. We start by allocating a new nonce for Alice. In Cryptis, we reason about this using the following rule. This rule says that the nonce that we generated is guaranteed to be secret. So we have the secrecy resource that describes terms that are not yet known to the attacker. We can choose if and when it will be revealed to the attacker. We also obtain a freshness resource describing terms that have not been used yet, that have been just generated. For the NSL protocol, the usage that we want to make of this nonce is rather simple. We always want the nonce to be secret, so we use this little proof rule that allows us to consume the secrecy resource to create a nonce that is permanently secret. In the paper, you will see usage of the secrecy resource that's a little bit more interesting and that allows us to describe dynamic compromise of cryptographic material. The next thing that we do is to encrypt the first message. And to do that, we use the following rule. This rule says that encrypting a term is safe provided that two things hold. Number one, the private key that matches the public key that we're using ought to be secret. And the reason for that is that we don't want the attacker to be able to read the contents of the message, because if the attacker were able to read the contents of the message, we would also need to show that the contents are public. We also have to prove that some application-specific encryption predicate holds of the contents of the message. For the NSL protocol, we're going to choose this predicate to simply say, for the first message, that the nonce that Alice is sending is public, which it is, because we have generated it this way. Once encryption returns, it is going to return a public term, which is good because we want to send that over the network, and we use this proof rule that says that anything public can be sent over the network. Then Alice waits for a response, which is guaranteed to be public because it came from the network, it have originated from an attacker, and then she's going to try to decrypt this message. To decrypt a message, we use the following rule, which says that anything public can be decrypted, and if decryption succeeds, we're going to be in one of the following two cases. One possibility is that the contents of the message are public. So this represents a situation where the message that we got was produced by an attacker. For the NSL protocol, however, we're checking that the message that we get back contains the nonce that we sent originally, which is good because we generated this nonce to be secret, which means that we can rule out this possibility. Which leaves us with the second case that says that the encryption predicate that we chose for the second message holds. For the NSL protocol, we want to use the following predicate, which guarantees that number one, the nonce that Bob generated is also secret, but number two, that some escrow assertion holds. So an escrow is a design pattern in separation logic that allows us to use a persistent assertion to trade in one ephemeral resource for another. And here we're making crucial use of the advanced, rich assertion logic that Cryptis is built on, that allows us to write these escrow assertions in the first place. In any case, once we have this escrow, we can trade in the freshness resource that we got for the nonce and obtain whatever application level resource we care about. So why is this useful? Let's consider how we might use this protocol at a high level. Here we have a simple application where we have some authentication step composed with a reliable communication abstraction and whatever application logic we care about. We might implement our authenticated key exchange using a protocol like the one I just showed you, where we use the cryptographic material that we exchanged to derive some kind of symmetric encryption key. Above that, we're going to have a reliable communication abstraction that is implemented using symmetric encryption, where we use sequence numbers attached to every message to guarantee that messages arrive in order and that they're also not duplicated. Logically, what that means, again, taking inspiration from this prior work, is that every message that we send and receive comes with an associated resource that is determined by whatever application we're verifying. Here we're using this so-called session escrow pattern that comes from previous work, which requires us, crucially, to mirror these sequence numbers that are stored in concrete program state in ghost state. And for this, we make crucial use of the fact that when we launch this handshake, we can exchange separation logic resources and coordinate their use, right? In particular, when Bob sends back some resource to Alice, he can allocate the initial ghost state used to store these sequence numbers, which is going to guide the use of the escrow pattern on the app communication layer. Once you have established this abstraction, you can use it to verify whatever application level property you might care about. For instance, if you're verifying a key value database, you might be able to show that you can manipulate the database as if it were local storage by using some kind of points to resource. And with that, I think I am at the end of the talk, actually. So just to wrap up, there are two key takeaways that I would like you to take home. One is that protocol specifications should really be designed with reuse in mind. The protocol is not something that you verify for its own sake. It's something that should be reused in a larger system, and the specifications should reflect that. And crucially, separation logic is a key ingredient for making this type of integration possible. You will see much more in the paper. We have more complicated protocols that we have verified, notably protocols built on Diffie-Hellman key exchange, which allow you to prove advanced security properties. In particular, they allow us to analyze non-trivial compromise scenarios where you have agents that can have some of their keys compromised and still get some interesting security guarantees of forward secrecy that hold in that setting. We also discuss how we use this methodology to do the end-to-end verification of a key value store. And of course, there's a bunch of future work that we'd like to do. We're working right now on integrating this with session types and actress, but also doing relational versions of Cryptis to prove even stronger the secrecy properties, and we'd also like to generate models, Cryptis models from running implementations. And that brings me to the end of the talk. Thank you.
Thank you for the very nice talk. So I am not an expert in verifying crypto protocols, but from what I know, there was a work done, and I think you quoted it by Leonard Arkind and his co-authors,
Yes.
Who took models in Tamarin and proved the refinement of those protocols at the level of the implementation in Go using Viper. So could you highlight the conceptual differences between what you have done and what they have done?
Yeah, so the main difference between our work and theirs is that they are concerned with this problem of how do you take an actual protocol implementation and verify it according to these protocol specifications that people have cared about. The main difference is that the specifications that they use are not built with reuse in mind. So they really didn't ask themselves the question of, well, now that we have these specifications, how do you use this for something else, like a distributed system or a database or something like that.
I'm very sorry, just to follow up, and which examples in your case demonstrate this reusability? I can look it up in the paper, but...
Yeah, so essentially in this diagram, you could consider that they stop here and that they have a specification that works for just this piece. The logic that we use and the case studies that we consider cover this entire thing.
Thank you.
Oh, thanks for the talk. So in symbolic crypto, the primitives are considered usually perfect, right? But you also have tools in Iris like Clutch where you can basically verify the primitives. Would it make sense to create some sort of connection between Clutch and Cryptis so that one can verify the primitives and the protocol within one framework?
Yes, so it's a pretty open problem in crypto to draw a strong connection between the symbolic and the more concrete computational model. And the main issue is that in the symbolic model, the specs are very clean, they're perfect, right? Whereas when you move to the computational world, everything is approximate and up to, I don't know, some probability of error at the very least. So yeah, I think we have to solve some more fundamental problems in crypto before we can start incorporating that.
Thank you very much. I was just curious about, can you say a little bit about the adequacy theorems that you prove? I mean, what kind of statements can you get externally in terms of the secrecy? I was wondering a bit about that.
All right, so the adequacy theorem says a couple of things. First of all, it says that it assumes that you prove a spec for a program in a context where you have a resource that allows you to define what application level encryption predicates you want to use when verifying a program. So you're going to use this resource to set up your verification. And after you do this, you get the usual Iris property that says that, well, if you have a pure postcondition, the pure postcondition must hold of the result. So by itself, this doesn't tell you anything about secrecy. The way you reason about secrecy is to say, well, let's set up a little game around my protocol where I have an experiment where the honest agents are interacting with an attacker. So the attacker should be able to, for instance, output the value of a session key on a public channel. And you can show by the rules of Cryptis plus adequacy that it will be impossible for the attacker to output this value, for instance.
Yeah, so I wanted to also ask about this perfect secrecy, perfect crypto assumption, and whether you could still analyze it with respect to a sort of perfect randomness assumption if you were to somehow incorporate like the number of times in which you use this assumption of perfect crypto, so that you know that you aren't in a loop that's going to try, you know, every possible option or something like this.
Right. I think that this is something that people have looked at to some extent. It's just not clear how it generalizes to all possible symbolic crypto primitives that you might want.
Thank you for the great talk. I'm just curious if you could say a few words about the underlying resource monoid that drives the separated conjunction. Like, what is it that you track in the resource?
Right, so there's two main components. One component we inherit from base Iris, and this is the part that we use to reason about freshness. So under the hood, all these nonces and cryptographic terms are implemented using heap locations in heap lang. So we use that to reason about freshness. But then on top of that, we have some higher order ghost state resources that we use to track these encryption predicates associated with terms.
Okay, thank you.
I'll ask. Quick question. Following on Lars's question about adequacy, with these protocols, often you need to make some don't you need to make some assumptions at the beginning about like keys that are known for the different parties? And if so,
Yes.
how do you discharge those assumptions?
Yes, absolutely. So so one thing is the verification of the protocol itself, right? So there you start with some assumptions. The way you come up with a ground truth statement to reason about the security of this thing is by wrapping it in the security game. And the game is responsible for initializing the state. So the game is going to allocate the initial keys. It's going to disclose whatever it needs to disclose to the attacker. It's going to compromise whatever it needs to compromise.
So that's sort of part of the operational semantics.
That's right.
Okay, in the interest of time, I think we'll stop there and thank Arthur.